computer. All right. So, sorry everyone, today we had some technical difficulty with sharing Dr. Nasrrddine Youbi's presentation, but this is going to be the recorded presentation with a small audience. We will have some questions at the end that hopefully stimulates thought and ideas. So I'm going to go ahead and introduce Dr. Youbi. Professor Nasrrddine Youbi was born in Fez, Morocco on November 25th, 1959. He is a full professor at the Geology Department of the Faculty of Sciences in Semlalai of Qadi Ayad University in Marrakesh, where he obtained his PhD in volcanology and geochemistry in 1998. He served as head of the Department of Geology for 2 successive terms from 2014 to 2017. From 2008, he was twice an expert with the scientific committees of the National Center for Scientific Research in Rabat. He is also an expert with the French-Moroccan Joint Committee of Hubert Korean Tubkal program for the 2nd term. And Nasrrddine Youbi is currently director of the Laboratory Dynamics of the Lithosphere and the Genesis of Mineral Resources, where he develops with his colleagues and PhD students research in volcanology, petrology, and geochronology. His research focuses mainly on large igneous provinces, such as the Central Atlantic Magmatic Province of Morocco, Portugal, and the United States, the Precambrian of the Anti-Atlas, the Moroccan Sahara and northern Mauritania, and the Permo-Carboniferous, Jurassic, Cretaceous, and Neogene quaternary volcanisms of Morocco. He participated with the French Geological Survey within the framework of the National Program of Geologic Mapping in the elaboration of 6 geologic maps in the Moroccan Masada and Anti-Atlas. Nasrrddine supervised several PhD theses in Morocco and abroad. He's an author of 100 publications indexed on the ISI bibliographic database, including 3 articles published in 2017 and 2020 in the prestigious scientific journal Nature. In 2019, he was awarded by the Prize for Excellence in Geoscience Research, a prize awarded to the best Moroccan researchers who were distinguished by the quality, volume, and number of citations of their scientific production, listed by the publisher Claravit Analytics Web Science Group for the last 5 years. So without any further introduction, I'll let Dr. Youbi give his presentation.
Thank you, Alex, for this introduction. I am very happy today to give this talk to the virtual seminar for Precambrian geology. I would like to thank Professor André Becker that I met in Tomsk in 19, and also Alex for the organization of this interesting seminar. So my talk today is the link of the Central Iapetus Magmatic Province, which is a large igneous province, with the circa 580 Gaskier glaciation. And I would like to draw your attention about 2 points. The first one is that my English is not so fluent, so if I am in the catch-22 situation, please help. And the second point is my talk is intermediate between for PhD student and specialist. And I am here also to have your question and to discuss ideas, if any new idea. So the outline of my, my talk first is an introduction, then I will talk about large igneous provinces, and then I will talk about glaciation, and then the Ediacaran Gaskier glaciation. Then I will talk about the Central Iapetus Magmatic Province, and the link between the SIMP and K with a proposed scenario, and then future work with some strategic questions. So this is about the Cryogenian and the Ediacaran period of the Neoproterozoic, from circa 720 to 539, using the new age of the base of the Cambrian, referred to Linnemann in Terra Nova and Landin in episode for people who are interested for the new subdivision of the Cambrian and also the Precambrian Cambrian boundary. So during those periods, many phenomena involve the poster and the geosphere, including supercontinent breakup, the assembly of Rodinia and Gondwana, respectively, emplacement of sizable large igneous province like the Franklin Province and the Central Iapetus Province. There is also measured negative carbon isotope with global significance, which is the largest carbon tail excursion in Earth history. We have also the first appearance of complex animal in the fossil record. Oxygen, like the Neoproterozoic oxygenation event, and also widespread glaciation, like the Stridian, Maronian, and the Gaskiers. Many explanations for the causes of the Neoproterozoic glaciation, and today I will expose the case of the silicic glaciation and its link with the SIMP. If you look at this slide, you can see here, we have at least 3 glaciation: the Stridian glaciation, the Maronian glaciation, and the Gaskiers. Note that the Maronian and the Stridian are considered worldwide. We have also the fossil record, and you can see that the fossil record is very weak when we look for the Cryogenian period, but the record is more important when we are in the Ediacaran, especially with the Ediacaran type fossils. We have, regarding lips, we have 3 main lips. We have the Franklin lips, which is related to Stridian glaciation. We have the Gaskier glaciation, which is related to the SIMP, and the Maronian could be maybe related to the Wundong lip in China. Let's begin by the definition of what are large igneous province. You can find this definition in the commission called Commission of Large Igneous Province. The leader of this commission is Professor Richard Ernest. So Earth is punctuated by a large volume of mafic magma, were generated and unplaced by processes and related to normal sea floor speeding and subduction. The lips are best preserved in the Mesozoic and the Cenozoic record, where they occur as continental fluid basalt, volcanic rift margin, oceanic plateau, etc. There are also felsic rock can be represented, but the most important thing to retain is that lips are large volume and they are unplaced in short time, and they are related to continental rifting and breakup. I will come back about more definition about the lips. If you want to know more about lips, there is this book of Richard Ernest called Large Igneous Province. And for your information, you can get this book from the library Genesis. It's free of charge. Here we have the main list of the past 500 million years. I can give example. For example, if we look at the camp, which cover several continents, we can find it in Africa. It's about 201. In Canada and USA, and also in South America, in Brazil. We have this province called the Central Atlantic Magmatic Province. We have also to the south what we call the Paraná Etendeca. The Paraná is in Brazil and the Etendeca is in Namibia, with an age and the North Atlantic Igneous Province here in Europe, here and here, between 62 to 555. And all these provinces are related to the, are the witnesses of rifting related to the opening of the Atlantic Ocean. The Central Atlantic Magmatic Province is related to the central part, the opening of the central part of the Atlantic Ocean. The Paraná Etendeca related to the opening of the southern part of the Atlantic Ocean, and the North Atlantic Igneous Province is related to the north part of the Atlantic Ocean. There are also similar large number back through in the Proterozoic and into the Archean, and there are also analogs on Mars, Venus, Mercury, and the Moon. So, we have the record of from the 4,000 to the actual, and between 20, 30 years, and similar to the rate of extinction. Regarding the importance of the lips, as it was in the definition, linked with regional uplift, they are linked also with the rifting and the breakup, or attempted breakup. We will see that they are linked also with ore deposits and oil, gas, and aquifer. And the most important, that they are linked with the mass extinction and rapid environmental change. Here we have classification of large igneous province. You can see that large igneous province can occur in continental domain or in oceanic domain, like oceanic plateau. But the most important thing is sometimes they are associated with carbonatite and kimberlite. And also some province contains mainly felsic rocks, and they are called silicic large igneous province. Here we have the link between ore deposits and the lip family. And you can see, for example, that the associated carbonatites are associated to niobium, tantal, and are can have more detail about link between the lip family and ore deposits in paper of Ernest and Jewitt. Lip can cause short environmental impact and sometimes leading to mass extinction. And this paper published in Petrova in 2017, which is like a resume of. So lips are linked to mass extinction, to global warming, to global cooling, to oceanic anoxia, to acid rain. They can release toxic metal like mercury, sea level change, oxygenation of the atmosphere, and here, I'm sorry, and here we can see the link between mass extinction. During the Phanerozoic, we have five mine extinction. We call them the big five. There is one in the boundary between the Ordovician and the Chile, one at the end of Devonian, another between the Permian and Triassic, and another between the Triassic, Jurassic. And you can see that usually there is a link between the mass extinction and the lip. For example, the Triassic to the Central Iapetus Magmatic Province. Let's talk with in Africa, we are in the most recent lips, and I already wrote this. There is this lip, the cap, related to the central part, the Etendeca, which is related to southern with this. And for and also the lip of Ethiopia and Yemen related to the of Red and Gulf of Aden. This is some information about the square, about the surface of these lips. And at the end, very important is, for example, if we take lip and you compare it with the first, for example, for the Atlantic Central, we have the first crust appear around 175, and the lip is about 200 to 201. So there is a period, some people estimate this period to 5 millions and other estimated to 30 millions. In the Caro, it was estimated to less than 15 million years. So sometimes knowing the exact age, of the lip, you can make a deduction for the age of the crust and vice versa. One word on a very famous lip is Central Iapetus Magmatic Province. We can find it, as I said before, in Africa, in South Africa, and also in North America. Yes.
I think we have some feedback from your mic, and I think maybe sometimes we get better sound quality if your video is turned off. Try to turn off just your video without turning off your audio.
I don't understand you.
So there's at the bottom left of the screen, you have an option to mute yourself and stop your video. I think that having your video on may be causing some issues with having good sound quality. So maybe try just stopping video. Just in the bottom left of your screen. Oh, it's actually, it's okay. Oh, okay, great, cool. Now continue. Okay? Yep, continue.
Okay, 1 moment. So if you, I'm sorry, if you look, for example, it's called the Central Iapetus Province, it occurs in Africa, in South Africa, and in North America, and also in Europe, in Spain, and even in France. And the best outcrop are located here in Morocco and in North Africa, because the yellow part that you see here, they are the only part when we can find lava flows. Let's come back to the glaciation. This is the maximum extent of Pleistocene glaciation. And you can see that one entry of land is covered by ice that you can see here, here, and here. This is a regional ice age. If you can see today, for example, today we have less ice in the north and in the south. And in the past, there are some situations when we have ice everywhere, ice at the equator and ice at the pole, and we call it the snowball Earth. You can find more information on the snowball Earth in this link that I put here. If you look in this slide, we have numbers indicate glaciation, and you can see that 500 until 500 we have snowball Earth, but after 500 we don't have snowball Earth. Some people interpret this that is related to high obliquity and low obliquity. If you look, for example, the Precambrian, we have snowball Earth during the Paleoproterozoic and also during the Neoproterozoic, and during the Neoproterozoic. This slide is taken from a recent paper of Hoffman, and if you see here in detail, the Sturian glaciation is related to the Franklin lips. There is also the Maronian, but the glacier is not considered as snowball Earth. This is the, if you want, we have the Sturian glaciation and the Marinonian, glaciation are considered as snowball Earth, but the Gaskier is not considered as snowball Earth. Here also, slide taken from a recent paper of Hoffman is the present distribution of cryogenian glacial and periglacial deposits during the Maronian glaciation, and here for the Sturian glaciation. The same, but in a reconstitution, in a global reconstitution, here the Maronian Sturian. And you can see that the Franklin, for example, lips there is a paper of MacDonald that link this province with the Sturian glaciation. Now, let's talk about the Gaskier glaciation. Here in this reconstitution, 580, it is taken from Lee et al. And also Hoffman and Lee 2009, but which is updated, especially for the Ouarzazate glaciation and the Tidilin glaciation. Here we have distribution of ages for the Ediacaran glaciogenic formation, and we can see that we have a peak at 580. Here, the Ediacaran Gaskier glaciation in Canada, and I would like to draw your attention. Diamictids are in this color, and I would like to draw your attention that the Gaskier glaciation, the name of Gaskier came from Canada, and also is the only place where it is well constrained by high resolution uranium plumb geochronology. Here is the compilation of the Gaskier glaciation in several blocks. in North Africa, in Arabia, in Avalonia, in Laurentia, etc. Based on compilation. And if you see, for example, here you can see in black the data of boring, and in the red the data of poo. So maximum duration of deposition of the Gaskier formation is between 2.6 to 1.6 million years. If you look at the Buena Vista Peninsula, the maximum duration of deposition is years. If you take Morocco, it spans about 6 million years. And we have two glaciations. One glaciation younger than 600, and another is about 580. This is the reconstruction of the continent at 600 with two options, high latitude option and low altitude options. And here I am placing the boundaries of the Central Iapetus Magmatic Province. This color is the late Neoproterozoic continental rift, and this is the Pan-African belt. And recently I achieved that this line could be moved until here to South China and Australia, because there are some SIMP outcrop in this book. So for me, this province is one of the largest in surface and also the thickest. If you look in USA, there are many but mainly dikes, worms, and seals. And you have some like for example, long range dike 615, Cetil intrusion 500, and it is well lettered. You have some rift like here, okay, and it's similar. We'll see that it's similar to Morocco and Baltica. If you look, there are two interesting papers on the SIMP. The first one is PUFER, American Journal in 2002, and another in 2011 by Michel Eta. If you would like to have more information about the geochemistry and the paleomagnetism of this province. And the geochemistry indicates the evidence of three geochemical groups. The first one is continental fluid basalt, is in blue. It spans from 615 to 564. We have the Ocean Iceland basalt, the green, it spans from 540 to 550. And the Morb group, this color, yellow, that could be Cambrian or Paleozoic. Note that this magmatism is interpreted as related to a plime located here in Southern Mountain Plume. Let's move to Baltica, especially the case of Ukraine. In Ukraine, there is a huge province called Volyn, and the mine pools are at 580 to 560. This province, here we have a stratigraphic column of this province. And It was mainly studied by Professor Leonid. And there is this reference for people who are interested to this province. This province is continental fluid basalts, and not that the Ediacaran fauna are overlying this province. So the series continues. The series that contains the Ediacaran biotopa are overlying the Vulin formation. I'm sorry. Here about the chemistry, and the chemistry is typical to continental fluid basalts with low Ti basalt and high Ti basalts. Here is the classic interpretation of the classic interpretation is there are two possibilities. So one possibility is that we have thermal lithospheric anomaly. Another possibility is to have plime or superplime. And here this schema explains how we can have high Ti basalt and low Ti basalt. Let's move to Morocco. This is the map of Morocco in the Anti-Atlas. And this color, called the Ouarzazate supergroup, is corresponding, this color, as you can see, it covers all the Anti-Atlas. It corresponds to the Central Iapetus Magmatic Province. We have also some Paleoproterozoic basement, but this color is Ouarzazate supergroup. It corresponds to the Central Iapetus Magmatic Province. And this province is well dated, but not with high resolution. You can see here, everywhere there is uranium plumb dating, everywhere, but no place is dated by high resolution geochronology. Here, I have made a compilation of uranium plumb geochronology in Northwest Africa, in Laurentia, and also in Baltica. And you can see pulses. This is the overall SIMP. And you can see, for example, for the overall SIMP, we have the first pulse is 603. The second pulse is 582, and the third pulse is 561, and the third pulse is 525. If we look at the Ouarzazate supergroup, it's a volcanic pile it's very thick, that can reach 3,000 meters of volcanic rocks and sedimentary, but they are separated by internal inconformities. And we can distinguish at least 3 eruptive cycles. The lower unit or the first cycle is composed with extensional calco-alkaline series, with volcanological characteristics typical to continental stratovolcanofacies. But be careful. This is calco-alkaline, but you can see normal faults. So it's like the basin and the range in USA. People used to consider what is calco-alkaline is subduction, but here in Morocco, the subduction is over, and the calco-alkaline is intraplate calco-alkaline. The second cycle, or the second unit, it occurs as volcanic pile of tholeiitic basalts associated with fluvial and lacustrine stromatolite also. And their volcanologic volcanological characteristics are compatible or facies model of continental basaltic succession, which is typical to continental fluids basalts. And the upper unit, or the third cycle, is represented by an alkaline, rhyolites, inembrites, lava flow, and domes. The volcanological characteristics are similar to continental silicic volcano. We can distinguish, based on the chemistry, the three groups. Here, for example, the calco-alkaline group. Here, the alkaline group. And here, in this area, the continental fluid basalt. Similar thing here, but in one area called the Warsaw dike swims. Here's some photo about the trip. You can see here volcanics, inembrite, and as I said before, the Ediacaran volcanic pile is about 3,000 of thickness and 3 successive eruptive sites: calco-alkaline, continental fluid basalt, and alkaline. Here, for example, inembrites of the first cycle. You can have what we interpret like relief moutonné here, and also some glacial surface. They have more. Look, for example, here you can see what we call relief moutonné. Here is my friend give details. This surface could not be tectonics. You can have also diamictite, and also, but it's not well illustrated in this. We can have some ice rafted debris. And the ice rafted are shifted by small normal fault. Here, detail of this glaciated surface, glacially eroded surface with striation. More important, you can have peperites. Pepperite is migrating between andesitic lava flow and soft sediment. You can form pepperite when we have interaction between andesitic lava flow and the soft sediment. And usually when you have pepperite, it means that there is water, but you are not sure if water is ice or only water. But if you associate this pepperite with the surface that I showed you before, you can say that they are witness of glaciation. You can see, for example, here is andesite and the sediment, and the litage or the stratification of the sediment is deformed, which means that the sediment was completely fluidized during the interaction between sediment and lava flows. Here, a possible interpretation. This is during the Tidilin formation. Then we have the Ouarzazate formation of Ouarzazate group with ice, with volcano. And then we have tillites and progradal deposition. And then at the end, transgression with shallow water limestone. Not to the scale. Here the same schema as before. You can see that this is the boundary of the Central Iapetus Magmatic Province, and these are glacial Ediacaran glacial deposits. And you can see that most of these glacial Ediacaran glaciogenic formation are inside the boundaries of the Central, which means that there is some connection between the SIMP and the Ediacaran glaciation. So the 580, so the pulse correlates with the last Precambrian glaciation, the so-called Gaskier glaciation. And there is of Robert Stern, who is called volcanic winter to snowball Earth hypothesis, which fit with our scenario that I will explain later. So the last pulses of the SIMP correlate with the end and the beginning of the glaciation. Here is our proposed scenario, assuming synchronicity. Sorry. The Gaskier was likely a short duration. It was very short glaciation. So if it is short, the event who triggered this glaciation should be also short. It could be an impact crater, but the age of the possible impact crater in Australia is not well. At this time, there is no age with 580, let's say. So we propose that the initial silicic circa 580 pulse of Ouarzazate event in Morocco helped to trigger the Gaskier glaciation, because there is, during the first pulse, we have some caldera, a giant caldera, with let's say 22 kilometers on 18 kilometers. So they are giant caldera, and so they are giant caldera are producing what we call super eruptions. And usually super eruptions are responsible to inject sulfur and trigger global cooling. Then after we have the second cycle, which is subsequent between 509 to 570, like continental fluid basalt. And usually continental fluid basalt, they release more dioxide of carbon than sulfur. And so they were responsible for the end of global ice age. If you see here, for example, we think that the super eruption of the first cycle was responsible to create the snowball Earth, and then we have volcanism with continental fluid basalt characteristics, with liberation of more CO2, and that triggered the deglaciation. So at the end, here are some questions that I would like to share with you. The main question is, test whether large igneous province influenced global glaciation, environmental oxygenation, and biosphere evolution during the transformational mid-late Ediacaran interval. This interval is very important, between 590 to 550. And the second major question is about to determine whether the circa 580 glaciation, the Gaskier glaciation, which occur at least in 14 different paleocontinental blocks, are they synchronous or diachronous with the Gaskier glaciation? Because the Gaskier glaciation is the only place well dated in the world, and thus reveal whether or not the Gaskier event is truly global or not global. establish whether the duration, geographic character, and geochemical consequence of this global Gaskier glaciation. There is another glaciation called the Charnokic glaciation. I'm sorry. Also, we need the refinement of the ages of the Ediacaran glacial deposits in different paleocontinents, such as in Morocco, the Tidilin and Ouarzazate glaciation, and the circa 580 pulse of the Central Iapetus by using high resolution, high precision chemical abrasion zircon, because the only volcanic rocks dated by high resolution, there is a paper of Wall et al. Published recently in Geology, and also at the end, study of melt and minerals to estimate the volatile cocktail such as sulfur and CO2 in rhyolites and basalts. Here's some suggested further reading. I can send to Alex this reference. Here to say thank you. It's a photo with me and Richard in Morocco, saying salam alek to Ulf, who is the geochronologist who do for us some dating. And also at the end, you are welcome in March 22 for the International Dike Conference and also large igneous province and Rodinia in Marrakesh in March 22. Thank you. Thank you.
All right, thank you, Dr. Youbi.
Thank you.
That was good. It was good to hear about the Gaskiers. So did anybody have any thoughts or questions they'd like to bring up?
Yeah, thank you, Dr. Youbi, so much for your presentation. I had a question. So for the sturgeon glaciation, some people have one mechanism that people have proposed is that the weathering of a large igneous province could actually draw down CO2 and lead to a greenhouse state. Do you think there was enough, given the very short duration of these events, do you think that's possible, or are we talking on too short time scales to make weathering a useful mechanism?
Yes, there is the paper of Cox in EPSL who they say that the weathering can trigger glaciation, but for this was maybe the case of the Franklin glaciation. But for the Gaskiers is a little bit complicated because first we don't know if it is global glaciation or only we are at the top of mountains. You know, because we have to distinguish between glaciation. We can have ice at the top of mountains. We don't know at this time is if the Gaskier was global or local, just in some place.
Okay, thank you.
Yeah, Paul.
Alex?
I'll go ahead.
Yeah, sorry, go ahead, Paul. No problem.
Yeah. I think we have to be a little bit careful about extending greenhouse effects of volcanism backwards in geologic time. So already in Gaskier's time, the sun is 2–3% dimmer, which means that the ambient carbon dioxide content of the atmosphere was 2 to 4 times higher. In Sturdian time, it's 6 or 7% dimmer, and so the ambient CO2 content of the atmosphere was 10 times what it is today. And therefore, the same amount of volcanic input would be proportionately less effective. On the other hand, the albedo effects would be unchanged. And so the McDonald-Wordsworth hypothesis for triggering the Sturdian glaciation was an albedo effect from stratospheric sulfate aerosol injection. And a key factor there was that the Franklin lip was intruded through a neoproterozoic succession, which is rich in sulfate evaporites, the Shaler group. And as a consequence, those lavas are known to be unusually rich in sulfur. It's interesting, and I think very critical to that model, that the ambient climate was already cool, because to have a significant climatic effect to albedo by stratospheric aerosol injection, it has to be at very low latitude near the equator, which the Franklin lip was, but you need a cool climate to lower the tropopause enough to make the stratosphere accessible to volcanic activity.
Thank you. It's a great pleasure to meet Professor Paul Hoffman. You are the father of snowball Earth. I'm very honored to have you in this talk.
Kirschfink's bulldog. Actually, James Walker. It's the true father of the snowball cycle is James C.G. Walker. Walker, Hayes, and casting paper.
And they just got you to do the heavy lifting.
All there in the last page. The classic 1981 paper on the silicate weathering thermostat. Last page. The whole snowball idea is right there in a nutshell. As a thought experiment. They never dreamt it actually occurred.
All right, anybody?
Yeah, Nasser, can you tell more about this, I'm not sure how to, Charterisk or 569 glaciation? Because
I don't have enough data about this. I heard this in, I saw this in project that I evaluate. But there are similar glaciation. There is a paper of Linnemann that I can share with you. You think that there is Linnemann working on the glaciation, the Neoproterozoic glaciation in Spain and Germany, and they found that there is glaciation younger than the Gaskier. I think 567, if I remember. And they said that there is another glaciation more recent than the Gaskier, and it occurred in Spain and Germany, and maybe in Ukraine. I don't know. But I can share with you this paper.
But where is the Charterisk? Is it in Germany? It's not.
No, it's not in Germany. Charterisk, I think, is in Ukraine, in Baltica. In a way, in Baltica. I saw this in a project that I evaluate.
I had maybe one more question, and just more thinking about the time span of the Gaskiers. And you were discussing how in Morocco there's evidence for about 6 million years, and and other places we only have it for 300,000 years. Now, what sort of could account for this? Is it just paleogeography of these land masses? That longer time period of the glaciation would have lasted longer near the poles than near the equator?
Thank you. Thank you. If you want, Alex, there is geochronology and geochronology. If you want just to date an event, you can date, but the sigma is 2 million, 3 million, could be 30 million plus or minus. Okay. But if you want to date an event, you need high resolution geochronology. And in this, the uncertainty is about 40 to 50,000 years. And we are lucky that the Gaskier in Canada is the only place where this Gaskier is well dated with high resolution geochronology.
Okay, so it's a question of error bars. Okay.
What?
It's more a question of error bars.
Okay, you are welcome.
Okay, thank you. Thank you.
Yeah. I am sorry for the connection. We are in Africa, and also I am very happy. I am very happy to have Paul Hoffman as. It's a big honor for us.
Yeah. Well, great.
Judy Poo, who dated the Gaskiers, was maybe one of Sam Bowring's last students. One of many exceptional students.
Unfortunately, it was supposed that I work with Samuel Borin, but he died. But I am connected with some people who works with him, like Adam Malouf in Princeton, also David Evans in Yale.
All right, thank you, Dr. Youbi, and our small audience for joining us. I'm going to post this recording, and so we'll see everybody next week for our own Dr. Mary Jo Brounce here.
Thanks for persisting, Alex.
Yeah, absolutely. Have a good one, guys.
Nasser. Bye.
Bye, everyone.
Bye.